Marco, thank you very much for the introduction. I'm very sorry, but my Spanish is very bad, so I have to present in English. I'm trying to learn. I'm Pat Wheeler from the University of Nottingham, and I've been asked to talk about some of the ways we work with industry in the area of power electronics. So what I plan to do is to introduce you to my university, the University of Nottingham, and my research group, which is the Power Electronics Machines and Control Research Group. And then we'll have a look at some of the things we do and some of the ways we work with industry in the UK and in Europe. But I'm not starting with power electronics, I'm starting with geography. Nottingham is here. So this is Great Britain, so the whole of this is the United Kingdom, and Nottingham is as far away from the sea as you can get in England. So we're in the middle of the country. And we're about 180 kilometres north of London. In England, 180 kilometres is a long way. Okay, I know in Chile it's next door. Okay, so that's where we are. And Nottingham is famous for a legend, the legend of Robin Hood. Heard of him. And also, we used to have a very good soccer team. In the 1980s, our soccer team was the best in Europe. Now it's in the 3rd division. Okay, we're a big university. We have about 42,000 students. We've got a very strong international presence. Our main campus is in the UK, but we also teach in China and in Malaysia. And we're a true university. We have arts, we have engineering, we have science, we have social science. But engineering, and we have medicine. Engineering and medicine are the two biggest faculties within the university. But I'm here to talk about power electronics. So I've talked about my university. And power electronics is a great technology. Everything from your mobile phone through to planes, trains, cars, ships. The one thing that all these applications have in common is that they need power electronics. So we have a logo, power electronics inside. The problem with power electronics is everybody thinks this mobile phone is for communication, and it is, but it wouldn't work without a power supply. It doesn't work if you don't charge the battery every night, and all that requires power electronics. But also when you want to connect wind farms, PV, solar energy, to the network, you have to use power electronics. But people see the windmills, they see the photovoltaic cells, they don't see power electronics. So that means that everyone in this room, when people start talking about any of these applications, from 1 watt to 2 gigawatts, you have to remind people that none of this works without power electronics. So if we look at the sort of areas where we're seeing growth in power electronics, I thought I'd start with renewable energy, the topic of the symposium. Okay, so if you want to connect wind, solar, geothermal to the network, you need to convert electrical energy from one form to another using power electronics. The whole of the future electricity network is going to rely on power electronics for the control and the stability of that network. As we move away from fossil fuels and we move to these renewable energy sources, power electronics will enable the system to remain stable. And that's a challenge in any country. It's a challenge in Europe because we have very high density cities which require a lot of power and we have to generate away from them. It's a challenge in Chile because you have a very long country and you may wish to generate at one end of the country and use power at the other. So it's something we have to do. But it's not the only application. Transportation. We're looking at electric cars, we're looking at more electric aircraft, We're looking at electric propulsion in ships. So all these application areas are using more power electronics to enable us to have cleaner energy and to still have the transportation systems that we're used to if we lose the oil and coal. But we also have power supplies. So we want to have very efficient power supplies so that we use less electrical energy. If you take your mobile phone and you find the power supply for that, you'll find the power supply gets hot. Yeah? You're just creating electrical energy and then you're losing it in heat. So we have to make these power converters cheaper so that people will buy them, but also more efficient so we use less energy. Industrial motor drives still use half of the electrical energy that is generated. It goes into industry to move conveyor belts for production and for manufacture. So we ought to be improving the energy efficiency in those applications as well. And finally, lighting. We've got lots of lights in this room. If we make all the lighting and the air conditioning more efficient, we will again use less electrical energy. So part of what we're doing is generating electrical energy, and as power electronics engineers, we have responsibility for ensuring we can connect new sources of energy to the grid, but we're also responsible for how that electrical energy is used. So we need to make that more efficient and to be a better citizen so that we don't need to generate quite so much electrical energy in the future. So I come from a research group called the Power Electronics Machines and Control Research Group, and we work in the areas of power electronics and electrical drives. So we work in a number of application areas. So we work in aerospace, looking at the more electric aircraft. We work in renewable energy, looking at the future electricity grid. But we also have some other areas. We work in automotive and marine drives, so looking at cars, looking at ships and boats. We also work with the physics research labs at CERN and in Los Alamos, looking at power supplies for particle accelerators and in areas around that as well. And we also work in industrial motor drives, how we make production lines more efficient. And we've got some big facilities. We can work up to power levels of 1 megawatt. We also do some fundamental science on reliability as well as the application-orientated work. So to do all that, we have lots of people. So we have, I think it's 16 members of faculty. So we've got 8 full professors and 8 associate and assistant professors. We have about 45 or 50 postdoctoral research fellows. So these are people who have a PhD but continue to do research. And we have about 65 PhD students. So we've got a lot of people. Lots of people cost lots of money. So we also have about £35 million worth of current research income. And that comes from the UK government, it comes from industry, and it comes from the European Commission. And I'm going to have a look at some examples of that next. So to make that amount of money, we need to work with industry. And this is just some of the companies we work with. So you might recognize some of the names here. Airbus and Boeing, I believe they make aeroplanes. Companies like E.ON, my colleague from Germany will recognize that name. GE, are another big company, and Alstom, who make generators and make the equipment that connects the generators to the network to generate electrical energy. Some of the names you won't know so well, but you might do in the future, because they're the companies that are coming in to connect renewable energy to the network and to look at these technologies as they go forward. We work with companies like Nissan, I've used as the automotive example. And then in power devices, there's some companies there, Infineon and Dynex are 2 you may have heard of. We also work with universities around the world. And one or two of you in the room know that I visit Chile fairly regularly. And when you look at the universities we work with a lot of universities in Europe, but internationally you'll see that Chile is our favourite country. We've been working with universities in Chile for 25 years now. So it's a very well-established link. We've had a number of people from Chile who've come to the UK, who've studied, who've done a PhD in Nottingham, and then have come back to Chile. And from Marco's comments earlier, I think some of you may have been taught by people like Ruben Peña down in Concepcion, and Roberto Cardenas up at the University of Chile, and Cesar up in Santa Maria, all of whom have PhDs from my research group. So we have some very strong links with Chile. Okay, just to show the sort of things we've done, we've worked, or are working with all the universities listed there. I'm not going to go through them because I'll get cheers from the University of Telco again. But those of you who are into, who've worked with universities around the world will know that publishing journal papers is important, and at the moment my research group has over 50 journal papers with co-authors in Chile. So we're doing a lot of work with various Chilean universities. And this is just a list, don't read this all, but this is just a list of the universities we're working with in Chile at the moment. So we're working with the University of Talca, University of Chile, University of Concepcion, and Santa Maria over in Valparaiso. Various different projects going on with the various universities. But main thing I was asked to talk about is working with industry, why we work with industry, and how we work with industry. We heard the first talk this morning from Corfu was the mechanisms for funding research and for supporting industry. And these are just some of the ways we do this in the UK. So I'd like to start with this. It's not a thermometer. It's not showing it's cold today. This is a thermometer about technology. So at the bottom here, technology readiness level 1 is a new idea. Your professor has had a stupid idea over breakfast that morning, and he's made that your project. Okay, that's TRL 1, a new idea. It might work, it might not. TRL 9 is a product. So technology readiness level 9 is something like this mobile phone. It works. It doesn't have any major faults. It's a product that a company is selling. And what we find with this is that there's different levels in between. So academic research is down here. Building something on a bench in a lab in a university takes you to technology readiness level 3, maybe technology readiness level 4. Industry work at the top level. So if we put the technology readiness level along this scale here, and we put the resources needed on the scale on the left there, we find that universities work in this area. Basic research and applied research, funded maybe by government, maybe by universities, and there's quite a lot of resource available for us to do this. Industry work down here. So they take ideas that are well developed and they make them into products. And that costs a lot of money. But companies do that because otherwise they have no product to sell. And then we have this problem in between called the valley of death, where good ideas in industry don't get any money, so they don't get, sorry, good ideas in university don't get funded, so they don't get into industry. Okay? Every academic in every university has lots of papers, lots of files in his office full of good ideas, and only one or two of those ideas ever get here, and we lose that value. So what I would encourage our colleagues at Corfu to do, and elsewhere, is to fund this area here in the middle, to create a bridge, so that more of those ideas get through into industry. And that is where people like myself and my colleagues here in academia, in a university, have to work very closely with our colleagues in industry to take good ideas that solve problems and to try and make them into products. So, we need some mechanisms to do this. We need some money. It's always useful. To pay some people to have a look at these ideas. And this is a list of some of the ways that we work with industry in the UK and in Europe. Right from really big centres down to a small PhD project with a little bit of money from a company to sponsor the studentry. So these things are all possible as long as you have power electronics to drive it. So that's where this project is where industry funds the university directly. They give us £500,000, about $1 million per year to do some research with them. Sometimes the European government gives us lots of money. So Clean Sky is an aerospace project. This is about putting more electrical systems onto aeroplanes. It's led by companies like Airbus and Rolls-Royce. And the European Commission in 2008 gave the aerospace industry 1.6 billion euros. It's about $1.8 billion. Okay? So the debt of a large country. It gave us that amount of money and said, go away and make air travel cleaner. Develop these technologies that you need. And so that's what we've done. So we're looking there at making the electrical systems, making the whole aircraft structure, making the engines on the aircraft cleaner so that the aircraft is more efficient and it will use less fuel. The next project is now called, it's an imaginative project name, it's called Clean Sky 2, and that's going to be 4 billion euros. So all this project told us is that we can develop lots of new technologies, but we needed yet more money to develop even more new technologies. So Nottingham University has been very involved in developing the technologies in there, and that's where we work with industry because government has given us lots of money to go away and do that. Nottingham University don't get this amount of money, we just get a small amount of money, but it's still a big project for us. So some examples of what we've been doing there. This one's quite an interesting one in the middle. We've been looking at putting electric motors in the wheels of an aircraft so that when you're at an airport, you don't use the big jet engines to move the aircraft on the ground. You use batteries and electric motors. So you can, on the ground, you can move the aircraft like an electric car. Okay? That saves you lots of fuel because aircraft engines are designed to make an aircraft fly. They're not very efficient at making it move around on the ground around the airport. So you can turn the aircraft engines off on the ground. It has two advantages. One, it uses less fuel, so that's good. But the second one is it creates less noise. So people living and working around the airport find that the whole environment is quieter. And that, in Europe, is very important. So, that was a European project. The next one I was going to look at is, again, aerospace. But this is looking at a smaller project. So we were working with Airbus and GE Aviation in the UK, looking at a very simple problem. When you land on an aeroplane, you need some landing gear. You need some wheels to touch you down. And this project was looking at deploying and retracting that landing gear. Okay, so you have at the moment you have hydraulics, and we were looking at replacing that with an electrical system because it's more efficient and it's lighter. But the systems have been developed over the years for hydraulics, so you have to think again about how you're going to design that system. So the UK government gave us a project with these two companies and the University of Nottingham to go away, think about this problem for 2 years, and to build some demonstration hardware with the idea that that will be used by Airbus on future aircraft. Still maybe 5 years away of actually going on an aircraft, but these things are beginning to happen, and it's been enabled by that government money. Finally, we do smaller projects where we design small parts of hardware and we work in industry. These are two that are very different. The one on the right here was funded by Infineon, and it was making a power converter very small. So So it's looking at making a power converter that had a footprint about that size, but is processing 20 kilowatts. So this was 20 kilowatts in less than a litre. Okay? And we were doing that using new materials, silicon carbide switching devices and things like that. So it's a very small box to process a lot of electrical energy. And Infineon wanted us to do this to demonstrate their new technologies. So that was good fun. The one on the left is nearer to market. This was a research project back in 1997. So one of the first research projects that I managed 20 years ago. And this is a product that will be launched in the US later this year. So this is taking power electronics and building it into an electrical motor so that you don't have a separate box for your power electronics. The power electronics and the motor is one unit. So that's an example of where it's taken nearly 20 years to go from a research project to a product. So I hope I've given you some ideas of the research we do at Nottingham. I hope I've given you an idea of the areas we work in at Nottingham University, and I hope I've answered the question of how Nottingham University, some of the ways in which we work with industry. One of the things I will say is that we do a lot of basic research, analysis, modelling, and practical systems. It's always easier to talk about the big practical hardware because that's things you can have nice pictures of. But we are committed to working with industry because otherwise our research is wasted. I don't want my research to sit on a bookshelf. I want it to be used in industry and to generate wealth and a better life for everybody. Okay, so thank you very much for listening, and I don't know if we've got time for questions, but I'm happy to take one or two questions if you want. Thank you.